The hypothesis of the ancient immeasurable explosion is widely accepted by many experts as the core explanation for the universe's origins, including the formation of stars, planets, and all forms of life, including our own. Despite its rather eccentric name, the term Big Bang effectively conveys the enormity of the event. Initially, the universe existed as a dense mixture of particles compressed into a space smaller than the tip of a pin. From this extremely small point, a massive eruption of matter occurred, known as the Big Bang, summarizing the process that unfolded over billions of years. However, despite the enduring popularity of the theory regarding the origins of everything, advancements in scientific knowledge have continuously questioned its assumptions. When NASA launched the James Webb Space Telescope, the largest and most advanced space observatory to date, researchers speculated that its observations would confirm the theory of the ancient cosmic explosion. Sadly, after just 1 year in space, the telescope amazed experts with its groundbreaking capabilities, offering extraordinary insights into the universe's past. The James Webb Telescope's findings have uncovered galaxies so ancient that they could potentially alter our understanding of the universe's beginnings. This unexpected discovery has sparked significant interest among scientists and enthusiasts alike. One such major revelation occurred when astronomer Rohan Natu, analyzing early images from the James Webb Telescope, accidentally discovered a galaxy that astonished everyone. This galaxy, named Glass Z13, appeared to be incredibly vast and dated back to just a short time after the Big Bang, making it older than any galaxy observed before. Natu's excitement was clear as he shared the discovery with colleagues on Earth, describing it as beyond anything astronomers could have ever envisioned. The James Webb Telescope, positioned far from typical interferences and equipped with cutting-edge technology, was designed to peer into the universe's earliest epochs, a period known as cosmic dawn. This time, veiled in mystery, represents the formation of the universe's first stars and galaxies. By studying galaxies from this epoch, scientists aim to refine their understanding of major cosmic phenomena, such as the roles of dark matter and dark energy in shaping the universe. Initial expectations for the James Webb Telescope's discoveries were modest, anticipating that distant galaxies would be observed in the years to come. Yet, the reality exceeded all projections. The telescope's images revealed galaxies of astonishing size, challenging existing models and sparking a flurry of debate. As scientists continue to analyze the data from the James Webb Telescope, the implications of these discoveries could be profound, ushering in a new era of cosmological research. The remarkable findings from this pioneering observatory provide a fascinating glimpse into the universe's past, propelling humanity's quest to unravel the mysteries of existence. As early galaxies began to emerge, researchers and onlookers found themselves scrambling to understand them. Could this collection of unusually large and brilliant early galaxies be illusory, possibly due to inaccuracies in the telescope's early observations? Or, if valid, could these galaxies challenge standard cosmological models, suggesting that the universe is far stranger and more complex than previously thought? The question remains one of how we can interpret how the precise universe we know emerged from a chaotic beginning. The early discoveries from the James Webb Space Telescope might ultimately reshape the foundation of cosmic history. These revelations concern not just distant galaxies but also our own existence in the universe. As Mark McCarran, a senior advisor for science and research at the European Space Agency involved with the JWST project, remarked, "You build these machines not to confirm the view, but to break it. You just have no idea how it will break." The JWST's view of early galaxies has been billions of years in the making but traces its origins back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still many years away from its launch. However, even in its early stages, Chief Ricardo Jan mentioned that his team had begun thinking about what might follow Hubble's legacy. Despite initial disagreements on whether to focus on Hubble, Jan was determined to see the extensive development of space telescopes. Fellow scientist and deputy director of SD Sky, along with a small team, started drafting ideas that would eventually lead to what became the James Webb Space Telescope. They noted that while Hubble would be historic, its capabilities would be limited by its ability to detect visible light. The JWST, on the other hand, would operate in the infrared spectrum, allowing it to see deeper into the universe. The necessity for the JWST became even more apparent in December 1995, when astronomers conducted the Hubble Deep Field observation. Contrary to expectations of detecting a few faint distant galaxies, the resulting image revealed a vast number of galaxies, stretching back over 12 billion years into the universe's formation. After more than 20 years of development and at a cost of around $1 billion, the JWST was finally launched on Christmas Day, 2021. The telescope underwent rigorous testing before reaching its critical space destination a month later. By July 2022, it was ready to begin its long-awaited first year of scientific observations, known as Cycle 1. Part of the JWST's initial mission was dedicated to high-impact programs, including the Cosmic Evolution Early Release Science Survey and the GRIS Point of Convergence Enhanced Program, both aimed at uncovering insights into the mysteries of the early universe. Astronomers devoted countless hours to scanning specific patches of the sky, searching for signs of early galaxies. They initially anticipated modest findings, similar to the Hubble Deep Field, but were in for a surprise. Stephen Bladden from the University of Texas at Austin, leading the SE project, believed that extremely distant galaxies would only emerge after multiple data cycles from various projects. However, to the astronomers' amazement, these galaxies appeared quickly. The record for the most distant known galaxy had been held by GN-Z11, discovered in 2015 with a redshift of 11. Redshift measures the stretching of light due to the expansion of the universe, with a higher value indicating greater distance. Yet, in the case of GLASS Z13, two independent teams, including one led by Rohan Natu, identified the galaxy with a redshift of 13, pushing the timeline back even further. In their quest for quicker results, researchers relied on simplified methods for measuring redshift based on brightness estimates, rather than time-consuming direct measurements. Despite their simplicity, these estimates revealed galaxies that were unexpectedly bright and massive, some already displaying a remarkable mass equivalent to 1 billion suns. The excitement didn't end there. In the following days, more contenders for the title of the most distant galaxy emerged, some with redshifts as high as 20, indicating that they existed just a short time after the Big Bang. These galaxies displayed circular structures, which were not expected at such early stages of galactic development. Moreover, another team found evidence of smooth, faint galaxies at a redshift of 10, less than 500 million years after the Big Bang. Such rapid growth of large galaxies challenges the assumptions of the standard cosmological model, lambda cold dark matter, LCDM. To understand this anomaly, it is crucial to revisit the components of the early universe. In the immediate aftermath of the Big Bang, the universe was a hot, dense soup of subatomic particles. Over time, as the universe expanded and cooled, helium and other light elements formed, leading to the creation of the first atoms around 400,000 years after the Big Bang. Approximately 100 million years after the explosion, conditions became favorable for the formation of the first stars, composed mainly of hydrogen and helium. These early stars, larger and more massive than modern ones, coalesced into proto-galaxies, organized by the gravitational pull of dark matter. However, the JWST's discoveries challenged this model, revealing vast, massive cosmic structures far earlier than anticipated. Stacy M. from Case Western Reserve University observed the surprising absence of smaller protogalactic components, suggesting that some of the observed galaxies might be closer than previously thought, hidden by dust and appearing dimmer and more distant. The discovery of these early galaxies raises important questions about the universe's origins, underscoring the need for continued investigation and revision of our cosmological models. Follow-up observations of GLASS Z13 in August 2022 by the Atacama Large Millimeter Array in Chile yielded uncertain results. Despite using brightness-based estimates, ALMA failed to detect key elements associated with GLASS Z13. As Pede Tom Beebe from Goya School, who led the observations, explained, this suggests that low redshift anomalies might be excluded. However, ALMA still attempted to observe the galaxy. This highlights the challenge of obtaining consistent data using the JWST's high capabilities. Rohan Natu, one of the researchers involved, raised concerns about the inconsistency of the situation, stating, "The good news is there's nothing identified. The bad news is, there's nothing identified." He also noted that JWST is capable of revisiting its own findings for further clarification. The most alarming possibility could be that the standard LCDM cosmological model may need to be updated. Michael Bohan Cullen, a cosmologist, emphasized the magnitude of this potential paradigm shift, stating, "These results are so unexpected and difficult to fit into our standard model of cosmology. It would be a genuine upheaval to accept it." One possible explanation for these findings is the modification of Newtonian elements, which challenges the existence of dark matter. The JWST's observations could lend support to this theory, as proposed by Mark McCarran. However, not all cosmologists are convinced of its validity. Another potential explanation is that early universe galaxies may have little to no buildup, making them appear more luminous and affecting mass estimates. This could also explain ALMA's difficulty in detecting glass Z13. Charlotte Brickley and her colleagues proposed that the JWST might be observing the most brilliant, energetic galaxies in the early universe, which could indicate extreme star formation conditions during that era. David Spergel supports this theory, suggesting that high-mass star formation may have been more efficient due to higher gas pressures and temperatures, possibly influenced by early gravitational fields. The rapid dissemination of JWST's initial findings reflects a shift towards advancing peer-reviewed studies, often shared through platforms like virtual entertainment. While this accelerates the spread of new data, there are concerns about jumping to conclusions before thorough peer review. However, it is unlikely that the high redshift galaxies observed by JWST will be invalidated, given the sheer number of such galaxies. This suggests that the early universe may be very different from what was previously expected. Bladden expressed confidence in the validity of the discoveries, stating, "The chances of cosmologists being totally wrong are very small right now. Astronomers are rushing to correlate subsequent observations with the JWST's findings." Nancy Levinson is currently evaluating approximately 12 proposals from different teams, seeking additional observation time for JWST, primarily to study high redshift galaxies. Given the excitement and significance of these early discoveries, confirming them is crucial. Projects like the Universe Web, led by K2T, aim to expand the known population of early galaxies by observing a broader area of the sky for extended periods. They hope to identify even more galaxies and possibly detect the primordial proto-galaxies, using the telltale signs of supersized first stars and massive cosmic explosions as indicators. Some estimates suggest that JWST could detect galaxies with a redshift as high as 26, just 120 million years after the Big Bang. Confirming even a small number of these high redshift galaxies would be a major accomplishment, as Natu has suggested. This shows that cosmologists are undeterred by their findings. The JWST has ushered in a new era of scientific discovery, and despite the challenges, the rapid exchange of new information has invigorated astronomers. Troy, one of the proposal authors, emphasized the importance of confirming these discoveries, acknowledging their profound implications for our understanding of the universe. New efforts to verify and further study these early observations highlight the importance of collaboration in advancing scientific knowledge. As the James Webb Space Telescope embarks on its mission to explore the cosmos, the discoveries it makes will undoubtedly continue to expand our understanding of the universe's origins and evolution. The telescope's exceptional capabilities offer a unique opportunity to delve deeper into cosmic history, uncovering hidden stories and mysteries that were once beyond our reach. The implications of JWST's findings extend far beyond the realm of astronomy, inspiring wonder and curiosity about the vastness of the universe and our place within it. As researchers continue to analyze the data from this groundbreaking observatory, they eagerly anticipate the next wave of revelations that will shape our understanding of the cosmos and the very nature of existence itself. Ultimately, the James Webb Space Telescope stands as a testament to human ingenuity and exploration, guiding us toward a deeper comprehension of our cosmic beginnings and our role in the universe's grand narrative.